Hello everyone. Welcome back. We will start our next talk. For the next talk, we have Pratik and Sneha giving a talk on Edge ML with MicroPython plus TinyML. Can we welcome them once?
Hello everyone, good afternoon. I'm Sneha Singh, currently working as an analyst at Deloitte USI.
And I'm Pratik Kumar Panda, a site reliability engineer at Red Hat.
And today we are here to present a talk on the topic Edge ML with MicroPython plus TinyML, where we will see real-time inference on under rupees 500 boards. Okay, okay. So quite a big terms on this first slide itself. So let's start with the how we will go through today's agenda. Firstly, we will discuss the definitions of each and every term, like what is HML, MicroPython. After that, we will look into how this is possible, along with all the steps by steps. After that, we will see the challenges and optimizations, and further, we will conclude with quick Q&A round. Okay, so let me start by asking a simple question. How many of you here are wearing an Apple Watch or Google Pixel Watch or have seen one in actions? Just quickly raise your hands. Okay, that's quite a small number. But as we all know that, one of the most impressive features of Apple Watch is fall detections. And it has sensors which detects when we have taken a hard fall and it automatically reaches out for help. As you can see on the screen itself, we have an image of Google Pixel Watch and Apple Watch. Here, when the device got to know that you remain immobile for a minute or 30 seconds so, it automatically reaches to the emergency contact list and they were notified about it if you didn't respond. And if you're all okay, then you have to just click I'm okay and you're all done. So in this every moment, every second counts because the time difference between immediate help and delayed help is very crucial. But here is the catch. This device cost upwards of rupees 30,000 to be precise, and it relies heavily on powerful hardware and cloud support. Now imagine if this device can be cost around rupees just 500 and we have all the features embedded in it. Sounds interesting, right? So this can be done with the help of microcontrollers like ESP32 or STM32. When we think of smart and connected devices, we often think of expensive hardware. But here, we can achieve this goal with the help of using these microcontrollers. So, two of the most popular microcontroller families for HML is ESP32 and STM32. So, ESP32 is a small, low-cost microcontroller, and it has a size smaller than the Matchbox even. But it's packed with features that makes it interesting for this kind of project. It has a dual-core processor, built-in Wi-Fi and Bluetooth module, and has a lot of pins to connect with sensors like accelerometers, vibration detectors, and microphones. Here, ESP32 acts as the central hub. It collects the data from sensors, processes it locally, and then triggers in actions like sending an alert or controlling a device. But on the other hand, we have our another microcontroller that is STM32. Here, STM32 is a family based on ARM Cortex-M processors, and it is widely used in industry. It has a wide range of options because it can used as a wearable for small gadgets, and it can also used as a high performance in industrial systems. So we have our both the microcontrollers covering both the worlds, be it a hobby related project or be it any industrial setups. Okay, so now by you have wondering what's special for this microcontroller, why it's so special. So the main reason is that it strikes the perfect balance between cost, performance, and flexibility. Firstly, they are affordable and accessible. This microcontroller cost just is very cheap, and it is quietly easily accessible for everyone to use. It has better connectivity options. ESP32 has a built-in Wi-Fi and Bluetooth module. On the other hand, our STM32 is quietly used in industrial interfaces for sensory and machinery. Both are designed with low power operations in mind, which is essential for battery powered applications. And they finally provide a both large ecosystem of tutorials, vendors, libraries, which make them an ideal platform to bring projects to life. And the last one is they are so flexible to program, whether you use C, C++, Arduino IDE, or even Python. Yes, even Python also. Okay, so far we have seen how ESP32 works and its features. But now you might be wondering, these are microcontrollers, right? They would need low-level languages like C or C++ to program. So how do I use Python with microcontrollers? And the answer is with the help of MicroPython. So what is MicroPython? MicroPython is basically a lightweight version of Python, which is typically designed to run microcontrollers like ESP32. So here, we are, instead of writing C, C++ code, we are using simple, readable Python scripts to control sensors, process data, and interact with hardware. And the best part is that it's just like regular Python. Even if you don't know MicroPython, it's all okay. Because you know Python, right? So you can start programming microcontrollers with the help of Python language. It's just that, what we can say, making a small devices accessible to run with the help of MicroPython. And it's ideal for IoT, robotics, and embedded AI. You can try it online without any board on this MicroPython website. So let's have a quick look of LED blinking example. Here we want our LED to turn on for a second and turn off for a second. And that's how LED looks like blinking, right? So, yeah. So, have a look at the code. We will import the required libraries. Machine.pin.iot tells the microcontroller that Y12 is an output pin. And now we run an infinite loop where we turn off LED and sleep for 1 second, and we turn on LED and sleep for 1 second. And it appears that LED is blinking. So now it's very simple and similar to what you write in Python, just with a few more simple steps, right? Okay, so far we have our ESP32 running MicroPython, which is great for controlling hardware. But you would think, why would I need ML? But let's think about fault detections. It's not just about reading sensor data. It's about recognizing patterns. Is this motion a normal step, or is it a fall? For that, we need our devices to learn and take decisions of their own. And that's where Edge ML comes in picture. So what is Edge ML? Edge ML stands for machine learning at the edge. So instead of sending from your device to a powerful cloud sensor for processing, we run our ML models directly on devices like ESP32, whether it's a smartphone, microphone, smartwatch, sensor node, etc. This makes our devices smart enough to recognizing the patterns and take decisions of their own. The biggest advantage is that it has speed, privacy, and independence. For example, in fall detections, we don't want to wait for the cloud. We need our devices to react instantly, right? So that's where, and as the data never leaves the devices, so it's also more secure. So in short, Edge ML is about moving intelligence closer to where data is generated. So now we got to know what is Edge ML is all about. Now let's look at some of the key drivers of HML. First one is latency. It provides real-time response, no round trip, and as our data never leaves the devices, so there is no slowness. The second one is privacy. It keeps the data local, reducing the chances of leak. The third one is connectivity. Uh, HML is basically can be used in remote areas, and it can be used in during network failures also. So it can work offline without internet also. The last one is power and cost efficiency. So we don't need to constantly stream data, so devices last longer on battery and save money on bandwidth. So where do we use HML in action today? Like there are many sectors we are using HML. For example, in smart homes and IoT wearables, for gesture-based control, smart assistance, and activity recognition right on the device. The second one is healthcare and wellness. So it's can used in heart monitoring or sleep tracking process. The third one is industrial IoT. So it can be used spotting problems in machines before they break, as well as anomaly detections for safety. The third one is agriculture. So it detects, for example, it detects crop disease on the spot without sending images to the cloud. And the last one is automotive and mobility. So HML is not just a concept, it's already embedded in many industries that we interact every day. Now, but how do we actually fit ML into such small devices? And that's where TinyML comes to the rescue. Now, I would like to invite Pratik to continue the session.
So yeah, let's first understand what is TinyML. So TinyML is essentially machine learning on ultra low power devices. That's the microcontrollers or some of the sensor nodes. So what it does is it combines model optimization and some of the efficient frameworks, and it brings the AI capability to devices that have some kilobytes of memory. And it also provides a feature that you can run some of the models for months or even years, because those runs on very low power, low cost, low power devices. So we introduced two different terms, EdgeML and TinyML. So you might be wondering what's the difference between those two. So essentially, TinyML is just a subset of EdgeML, whereas TinyML is specifically focused on microcontrollers and any resource constrained devices. So whereas EdgeML can run on any of the devices that are on the edge, whether it could be smartphone or laptop, anything that can process a ML model. Now, some of the tasks that we can do with TinyML is classification, like detecting what's a fall or not, the example that we discussed, or some regression, anomaly detection, anything small enough that is efficient for the microcontroller. Now let's have a quick look on the TinyML software ecosystem, because this is the one that we'll be using. So the most popular one here is the TensorFlow Lite that's used for microcontrollers. Then you have Edge Impulse. So Edge Impulse provides you an end-to-end framework. So what you can do is essentially take your data, train it, quantize, convert, and deploy without needing to follow the manual process. You also have emerging trends like uTensor or MicroTVM. Some of the tool chains that you can also use is the Arduino TinyML that uses the Arduino platform and just combines the TensorFlow Lite with it, such that you can run on the Arduino devices. You have MicroPython that we'll be discussing with the ML libraries. And there's a new CMSIS neural networks that's optimized for ARM processors. That's the STM32. So we covered what are the topics, what's the definitions of them. Let's look into how we actually do it. So this is the pipeline that we follow. So, and essentially as simple as what normal ML pipeline looks like. So we'll first do the data collection, then we'll look into the feature extraction, training the model, converting and quantize so that it's used in the microcontroller, and then some deployment and inference on the edge. So let's start building. So setting up our circuit. So what sensor we'll be using here, and we'll be following the same example that we discussed in the initial part. That's this example for fault detection. So what we'll be using is an accelerometer. And if you look at the circuit, this is on the tiny board that I have here, and it's the same that you see in the picture. So essentially it looks like this. You just connect two of the two pins for the data that you need. That's the SDA and the SCL. Two pins that are connected to 5 volt and ground. So just 4 connections that you need to get your circuit started. Moving to step 1, we'll start with the data collection for MicroPython. So what we do is import the libraries. We'll define some of the terms like the sample rate, interval, how many duration we want to collect. So here I am collecting my data as labeled as fall, because I know that this data will essentially belong to something when a fall is detected. But you can collect your data at once over a longer duration, over multiple fall and no fall scenarios, and then you can label it accordingly. There's a simple class for MPU6050 where it has the init, and then it also gets the accelerometer readings. Just to give a heads up, what's an accelerometer? It just measures what's the acceleration in each of the x, y, and z directions. So so acceleration, again, the change of velocity. So moving to continuing our data collection, what we'll have is we are initiating the I2C. I2C is the interconnected communication protocol. For those who don't know, it combines. So instead of using multiple pins, you essentially have just 2 pins that we discussed, the SDA for data and SCL for time clock. And then what it is doing is it is collecting all of the values across X, Y, and Z axis, and that is storing out into a CSV file, and the file name is discussed in the previous slide. If you look at the sample data, this can look something like this. You have these sample numbers, then you have the acceleration. So if you look at 1 to 4 samples, the acceleration fairly remains the same, but then there's a sudden change. So that detects that there's a change in the acceleration. So that can be of a fall scenario, and then it again returns back to normal. Moving to the second step, so here we'll look into feature extraction. So what we want to do is, there could be a lot of noise in our data that we collect from sensors, and there could be some wrong data as well. So what we want to do is, we want to filter, we want to ensure that the data that we use is good enough for our machine model and machine learning model. So what we do is, we get the features. So what features are? Essentially numbers that we derive from the raw data to make sure that we have good processing data. Now, here if you look, the line number 6, it says return np.concatenate. What we are returning is the values, raw values of AX, AY, and AZ, so that model can learn from the temporal patterns. Then we are also returning the magnitude mean, and then we are also returning the magnitude standard. That's the variability. So that helps us to detect sudden jerks or smooth walking. So as an example, what would happen during a fall is, there's a sudden high magnitude, so the mean shoots up, and then also there's a sudden high standard in that short window. So if then we move to step 3, that's our model training. So this is a very simple model train, and it takes our input as 50 samples across all the 3 axes, and then it gives out 2 output as fall or no fall. Simple TensorFlow workflow that we have, and it is similar to how you do the machine learning training. This is an interesting step, and a step that comes after your normal machine learning workflow. That's converting and quantization. So what we want to do is, these machine learning models can become large, so we want to make them smaller. So what we do is, we enable some post quantization, that is optimizing the weights, and that is something that we can shrink the model and speed up the inference. So if you look, there's we use an inference input and output type as tf.int8. What it actually tells the tells TensorFlow or to convert is, you use signed 8-bit integers. So ESP32 and generally most of the microcontrollers, they do not have the processing power or floating point hardware. So however, they handle this quite easily, because if you look at the data that we got, sample data, it can be if you remove the decimal point, even that also shows that you are handling quite a lot better on the accelerometer readings. So instead of storing weights as 32-point bit, we are storing it as 8-bit integers. So what benefit does it bring? So this time the model shrinks 4 times and inference gets faster. Now moving to deployment. It's a bit tricky with when you want to deploy something onto such hardware. So directly deploying a TF-Lite file will not work. We want to convert it something that the machine understands. So what we'll do is we'll convert into, use one of the tool called XSD to convert into a C array with model. That's kind of a header file. And then we want to create one of the fault detections scripts. So if we look at the if the gen fault detect.py, it just says that if there's a huge change, you just print or blink the LED, and that we are converting using the TensorFlow Lite into something that is understandable by the understandable by the microcontroller. So the script is linked at the end of the slide, so you can always look into it. Then we look to Flash with ESP IDF. So what is ESP IDF? It's just the ESP framework providing some of the tools to do the flashing using Python. Now let's move to inference and see how this works in real time. So just give me a second. I think, okay. Let me change this. Okay. And okay. Yeah. So yeah, this is a short demo of what is happening. So if you look, when I'm holding the device at the top without any movement, it starts to predict that there's no fall at that point of time, and each prediction is at every second. Now, when the sorry. Now, when the device falls on, or move it very fast, it kind of moves again, and then it predicts that there's a fall. It predicts the same thing for 2 seconds because of the sensor reading that it gets. And then once it is back, it kind of moves back to the, and when I try to move it back, you see that even though I'm moving the sensor upwards, it does not say that it has fallen down. Instead, it just says it predicted no fall, because this direction of change is reverse, as well as the fall is as well as the speed is slow. So that's the inference demo that is based on the training that we did. So now that was the demo covered. Now let's look what are the challenges that we have faced. So with this kind of devices, the main thing that comes is the resource constraints. So you do not have huge megabytes or gigabytes of resources, memories, CPU, processing powers. You just have few KBs or max to max MBs. Then you have power constraints. So these generally run on 5 volts. So you need to have that ready. Then there we have the model size and accuracy trade-off that we saw in the previous section, that when we are trying to convert, we remove some of the floating point integers. There's deployment complexity. So you cannot directly take something that's on ESP32 to STM32. There might be some tweaks required. As an example, if you look at that code, it says that there's some issue uploading to the port because it could not be found, or there was some unhandled exception. Now, if you look, there's the hardware diversity. So you have ESP32, STM32, and then STM32 has more set of I would say microcontrollers, different use cases. ESP has also kind of ESP32 has 4 or 5 variations of it. So what optimizations can we do? So we want to do a co-design approach. So we want to ensure that whatever we are doing is done on when we decide what's the hardware, the software, and the ML model that we want to run. So these are not large devices. These are for specific specific use cases. So something like fall detection or something like gesture detection are the best approaches for using these small devices. Some things that you can also use are model compression. So how we did the quantization, that is something that you can run based on your model that you need. Using some of the efficient frameworks like TensorFlow Lite Micro, Edge Impulse can give you quite a bit of good ML model that is suited for this. You have hardware acceleration for some of the devices. So this device is a Arduino Nano 33 BLE. So this comes with machine learning enabled on it. So if you have this, you can run even higher devices. But that also comes with the cost factor. Uh, Power management, you need to be aware that whatever you are using, it needs to have proper power and backup for a long period of time. And then hardware ever co-design. So one of the optimizations that you can run. So instead of running the model at all times, what you can do is only run it when the sensor detects something. So that optimizes it for the processing stuff. So what's next? What can you do? Maybe look to explore edge impulse. Maybe some try to explore on the models that we build, try to improve those. You can also build something like a person versus object detection. So nowadays doorbells have this. So when you look at doorbells using this same feature, that is something that you have. And maybe try to explore the other boards that you can use. Arduino Nano 33 BLE is one of the examples that provides you with better hardware. So that's it from our end. Thank you, everyone. You can connect with us on LinkedIn or GitHub, and we can take the Q&A right now or maybe at the IT. Thanks, everyone.